Okay, so we'll start. This time we have one of our own, Omar Matus. He was a student here at the Universidad of Ibañez. He did the master in engineering science here. And he presented today a work he did with professors Javier Barrera and Moreno called Calibrating a Telecommunication Network Model with Dependent Failure. Thank you very much.
Thanks for the introduction. I'm gonna present. We can see first what we talk in the presentation. First, I'm gonna talk about the telecommunication network models. Fast review of how we can use that. After that, I'm gonna talk about network reliability. Marshall Olkin Model using Marshall Olkin Copulas. After that, I'm gonna talk about optimization models to calibrate the Marshall Olkin model to estimate the reliability. And finally, I'm going to talk about some experiments to validate the model. First, we can understand a telecommunication network like a set of components that basically send information from one component to another. That is very simple explanation, but it's good. And in telecommunication networks, we have some different measures from different users. For example, the clients always are measuring the speed, the providers see the cost and the connectivity and others. And when we design telecommunication networks, we have some constraints. For example, budget constraint, technological constraint, and geographic constraint. And for solve the problem, usually we use simulation or optimization models. That is the actual situation of the design in telecommunication networks. We have in this side the empirical dependency. In the papers, we observe an empirical dependency. The dependency exists, but we don't consider in the models for design, not for study. We have failures models like the beta model, independent model, and others, and we have design models. The idea of the work is take a failure model, calibrate, incorporate empirical dependency, and use to design model. Use in the design of networks, telecommunication networks particularly. And some works about that is the work of Barrera and Eduardo and Song et al. The goals of the work is first select a model. We have a list of models. We select one. We create a methodology to calibrate the select model, incorporating the dependency, obviously. And finally, we evaluate the calibrate model. It's important first take some assumptions in the models. The first is we want to work in a network represented by a graph with n edges. Yes, that is important. And we have three initial conditions. The first is the nodes don't fail. Always the edges fail. The second is the edges can have two only states, operative and non-operative. And the third is at the beginning, all the nodes, all the edges are operatives. The edges are the component of the system, and the nodes are the other thing of the network, at the telecommunication network. And we are studying, in that moment of the work, the ST connectivity. Yes, that is, the system is operative when I have a path between the node S and the node T. Yes.
So as you're fixed, you're fixing two nodes and
yes. Yes, no, just for two arbitrary nodes. Yes. how we can estimate or calculate the reliability. The first is use the approximation, the basic model of probability. Yes, we take the path when the network is operative, and we estimate the reliability using that. That is the classical form to resolve the problem. And we can change that and use a model, a continuous model, to represent that. Yes, we assign for each component a exponential variable that represents the lifetime of the component. Yes, and we choose a moment to see the network, to study the network, and we can in that moment we can in that moment assign operative or not operative to all the network. Yes, in particular we choose t equals 1, but it's arbitrary. We don't have, we can choose 2, 3, 4, it's not important, and we take the lambdas for do that. For recover the original model, we need to do lambda e equals to minus log of the marginal probabilities for each component.
Can you just explain that subset? What is it? X 5x.
That. Yes, this is a sum of each configuration when the system is operative. Yes.
So the phi function is
the phi function is the partition function that indicates if the system is operative or not. All the system, not component. Yes, using the ST connectivity. Yes. This is the binary function to see if operative or not. Oh, exactly. And we have the two models, and after that we can define the Marshall-Olkin models. The Marshall-Olkin model uses the copulas of Marshall-Olkin, and the more easy way to see is see an easy example. For example, I want to take two components. Yes, it's the more easiest case. I take two components and I define three Poisson processes, three chokes of the system, independent. First, N1, N2, and 1, 2. Yes? The choke associated with the N1 Poisson process affect the component 1 and change their state to no operative. Yes? The N2, the same for the component 2, and the choke associated with the Poisson process N1, 2 make that the both components change their state to no operative. Yes, it's important the Poisson process associated with N1, 2 because that process is, in abstract concept, the dependency of the components. And if we have that Poisson process, we have independent random variables for each choke. In this case, zeta1, zeta2, zeta1, 2, and we can define the lifetime of the component. Yes. In this work, we assume now first the marginal probabilities of failure for each of the components in the system, and second, the correlation between the component failures. We know that. Yes, it's parameters. And we use to calibrate the Marshall-Olkin model. We can, for the case of two components, obtain one equation for each marginal probability failure and one equation for the correlation. In this moment, we have three equations and one condition that the rate must be positive. And we have that system. That system is the calibration of the Marshall-Olkin model with two components. Yes. I can use that to go to n components and define all the chokes for each component and all the chokes for each pairs of components. And I will obtain that. Yes. In this moment, I have one equation for each component, for each marginal probability of each component, and one equation for each correlation between pairs. I have the same number of equations as variables. Yes, and that is not very good because, for example, if I take the probabilities and the correlation symmetrical, I obtain that relation for the row, for the dependency, the correlation in this case. Yes, and the correlation is between 0 and that expression, and that expression is very restricted because you see that the p is always like an order of 10 raised minus 4 minus 5. That is like 1, and that is like n. And if I have 50 components, there is a problem because the row cannot take very high values. Yes. What I do in this moment, I don't have more, but I have an option. I can define more chokes in the system. Here I only have chokes for each component and for pairs of components, but I can define chokes for every set of components. Yes, all the subset of components have a choke, and that is the idea. I'm gonna take all the possible subset in the system, and for each subset, I'm gonna define a choke that affects all the components of the subset. In this case, when a choke affects a subset, all the components in the subset change their state to no operative. And in similar way, I'm going to obtain that equation, that system of equation, that restriction here. This is a very important moment. I have one equation for each correlation in pairs and one equation for each marginal probability. I have an order of n² equations, but I define one choke, one lambda for each subset. I have an order of 2 raised n variables. I have more variables than equations in that moment. And I have the condition that the rates must be positive. There is 3 options, obviously. I can have unique solution, infinite solutions, or no solutions. Yes, and I can solve this problem using a model like that to minimize the relative error for each equation, or that minimize the absolute error. Yes. In the worst case, if the system has no solution, maybe the minimus is not 0, but I obtain a set of lambdas that represent the best possible equations. Yes. If I have infinite solutions, it's important to know, in this case, in both cases, if all the solutions give us the same reliability estimation. Yes, because the problem is solved. I have a solution of an infinite set of solutions, but it's important to know if all the solutions are equal in terms of reliability. Yes, and for that we study the extreme cases. Yes, I'm gonna take two solutions of the system, of that system. I'm gonna take two solutions. The first is the solution using only 1 and 2 components copula, and the second solution is take 1 and all components copula. Yes, the two are solution of that system. That's, and obviously here it's 0 the function, the optimus. Yes, but the problem is if I take the two solutions, I obtain different reliabilities. Yes, I have infinite solution. I take two and use one or use the other. We obtain different estimation for the reliability. Yes, and that is a problem because I don't know what solution is the better of the solution. Yes, I have infinite, but I don't know which of that is the better. And that is the case of the series system, and in the parallel system we see the same structure, taking different solutions of the same problem with the same marginal probabilities and the same correlations. We obtain different reliabilities. There is two important conclusions in this experiment. The first of them is that the independence assumption, it's not clear here, but the independent assumption doesn't overestimate or underestimate the reliability. Yes, it's not, I don't know when I use the independent assumption if I have more reliability or less reliability. I don't know. And the second is that different set of copulas, different solutions for a given marginal probabilities and the given correlations give us different reliabilities. And that is a problem because in the infinite solutions, I want to choose one, the better of the solution to estimate the reliability. I want to choose one solution that not only satisfies the system of equation, not only satisfies the system equations, but I need that solution was the better of the solution. Yes, to estimate the reliability. And for choose the better solution of infinite solutions, I take some criteria of the failures. Yes. In particular, we studied empirical data, but not really. We studied papers of the empirical data, and we obtained two behaviors. Yes. The first is the quantity of components. There is very logical the behaviors. The first is the quantity of components. Its failures affecting more components are less likely. Yes. If I have two subsets, one with 4 components and one with 10 components, the simultaneous failure of the 10 component is less likely than the simultaneous failure of 4 components. And the other is the distance between 2 components, that more distance imply less probability of failures. Yeah. With that 2 criteria, we can make a methodology to calibrate the Marshall Olkin. And that is the algorithm to calibrate the Marshall Olkin. First, I'm going to take the input. The A is the Boolean matrix in that system of equations. Here is I take the B is the right side of the equations. I take E is the error, and take B, that is the component, the copulas, to satisfy the distance criteria. A only includes copulas that appear in B because B is the criteria, it's the criteria of the distance between components. And I start with n equals to 1. N equals to 1 is the similar case to take the independent model, and I solve the one of the models, the minimization of absolute error or the minimization of relative error. Yes, I solve and I see the optimum, and if not satisfy me, I take n equals 2. In this case, n equals 2 is take checks by each component and checks by every couple of components. I do the same. For example, it's not good the solution. I take n equals 3. I take 1 check for each component, 1 check for each pair of component, and 1 check for 3 set of components. And I do that a maximum of n times, obviously. Yes, the distance is considered in the B. The B is a vector that contains only the copulas that satisfy the distance criteria. But the distance criteria, we can select basically 2 ideas. The first is the real distance, geographic distance, and the second is take the graph distance. In our case, we do the both, but in that moment we are do the experiment with the graph distance. If the edges use the same nodes, we consider that that copula can be used. And we do an experiment. The idea of the experiment is take a physical model and estimate the reliability of the network using the physical model. We call that reliability the real reliability of the system. With the data of the simulation of the physical models, we can calibrate the Marshall-Olkin Copulas model, and we can simulate and estimate the reliability using Marshall-Olkin Copulas model. And after that, we can compare the physical model, the real reliability, with the Marshall-Olkin reliability, and with the independent reliability. For that, we take a geographic correlate failures model, like that. It's like a earthquake factory. We start to throw earthquakes in the graph, and the nodes start to. For each simulation, we use one earthquake, and we estimate the reliability. In simplest words, the nodes, the edges more far away of the earthquake has less probability to fail. And we consider that network for the experiment. And we study the connectivity between the nodes 1 and 12 in this case. We do, we take 10 rise 6 simulations of the physical model and the Marshall-Olkin model, and the error is an order of 10 rise minus 3 for each simulation of the reliability, for each estimation. And that is the result. I can explain the table, obviously. For example, I take an earthquake with magnitude 5, not Richter, but it's and magnitude is equivalent. And I have the physical model. The physical model gives us a reliability of 0.84, for example. If we use the classical independent model, we obtain a reliability 0.93. And we can use the Marshall-Olkin model, for example, with maximum component for set of 2. That is copulas of 1 and 2 components. And with that, we have 48 copulas, and we obtain a reliability of 0.77. That is not really good. But if we take 3 components per copula, we can take a reliability of 0.84. That is very close to the real value. There is the same in the confident interval.
Can you explain again what is the first column?
The first column is the magnitude of the intensity of the earthquake.
How does it translate to failure?
Using that model. There, here, the D is the yes, it's exponentially distributed like the earthquakes.
Okay, and what is the physical model?
The physical models, the name of the physical model is geographic correlate failures models, and consider only that. We modify the model and include the variable D with the intensity of the earthquake.
That's the second column in your thing.
Yes, that is the real reliability. Because it's the reliability of the physical model. It's not real. We put a name, but
reliability. You simulate directly the geographical model, and you compute for each scenario if it is connected or not connected the network. And for example, for intensity 5, for the 84% of the scenarios, the result is that the network is still
But there is also an error associated with that, right? It's simulation.
Yeah.
Yes, yes.
So it's not like
Nothing like the real. No, it's a simulation.
same with the other one. There's also an error associated.
Yes, if the model is a bad model, it's a bad reliability. Yes, no problem. But it's interesting to see that the reliability is that reliability is very close to that reliability of the market.
There's no reason to expect that number would be exactly equal to
No. Maybe the real is 0.85 and yes, we have an error like a order of 10 raised minus 3.
Factor could be a statistical test, right?
Yes,
Yes.
yes, perfect. We have a confidence interval, and we see that the result is that the result. Yes. And that table is using relative errors, and we can use the other model of absolute errors that were better than the other. And for example, in the case of 5, we only have to take, for example, 2 maximum size of maximal cardinality of the copulas to have a reliability of 0.85. For example, in the other case, have 0.85, 0.85. Yes. And the independent model, in this case, is 0.93. It's far away of the 0.84. Yes. In this case, the independent model overestimates the reliability. Yes. But this is not always in this way. Many cases with the independent model can underestimate the reliability. It's just case by case. The actual words, we are use column generation to solve the problem. You can see that we have a model with a big number of variables and not very big number of equations. And one idea is use column generations to calibrate that.
So, just to make sure, I assume there are situations where you don't have the second column, right? Otherwise, why would you need the second column?
Because why I don't have.
But I mean, I guess in some cases you don't have the real model, as you call it, right? That's why
yes.
The copulas, right?
Yes.
Is that true? In some cases you don't have the second column. Some.
No, always I have that column.
So why do you need?
Because we are only do that experiment to confirm that the calibration is working, because some cases I only have the correlation and the marginal probabilities. I don't have a model in background. For example, in a network operative, I can obtain the model of that network. I obtain the data, and the data is marginal probabilities and correlation. Yes, in this case, yes, I have the model, I can use the model.
What?
Yes?
In those cases, you don't have a second column. Do you have a rule of thumb to say, okay, this is the number of copulas that I'm going to take in order to calibrate the model?
We think that exists a relation between the function, that function and the estimation of the reliability. For that, we stop when we obtain an error less than arbitrary error. We are studying that. And we use column generation to solve the problem, and the other is use general splitting to simulate the Marshall-Olkin calibrate model. That is for rare events. Yes. And in conclusions, we can say that in that experiment, the proposed methodology estimates at least twice better the reliability of the system and the independent model. That is good. And we use only an order of n squared more equations and variables to obtain that. Yes. In time cost, we need twice the time necessary to do the estimation using independent model. Yes. Obtain twice better reliability using the twice of the time. In conclusion for that example. That is. Thanks.